happens. We're getting audio only today, people. We'll see how it goes. All right. The other name for this course is vector calculus. So let's talk vectors. How many of you have taken physics class? So you've seen vectors. So most of the next couple of sections will be familiar. We did a bunch of this in trig as well, but we're going to do it here. Vectors are oriented segments. They contain magnitude, length, and direction. So in one sense, a vector is a multiple dimensioned quantity as opposed to a number. If we have a set of points, A, B, then I would say that that's an initial point. And B is a terminal point. And so a vector. On the blank chalkboard like this, that really doesn't help me very much. It goes this way, right? So let's put this back on the Cartesian plane. Well, in that case, I need the initial point and terminal point coordinates. So let's go with the point at the origin and then the point 3, 7. Right? You can draw that vector. You can plot those points and connect them. If the point C, though, is -2, 1, and the point D is 1, 8, let's look at AB and CD together. So the point A is the origin. Point B is 3, 7. There's AB. That's a really bad looking 7. Let's try it again. There. Where's CD? Put it on there. All right. Say again.
C is -2, 1, and D is 1, 8.
Except for my crappy artistic ability. Let's think about these two vectors. I claim these two vectors have the same length. You agree with me, or am I talking out my ass? I claim they have the same direction. You agree with me, or am I talking out my ass? Well, if that's the case, then really, these are the same vector. A vector is independent of the points it occupies. We're only talking about its length and its direction, and those two vectors have the same length and the same direction, so in that case, AB is equal to CD. As vectors, they're exactly the same, which means I can make infinitely many different copies of the vector AB, put it anywhere I want, any initial point at all. As long as it had the same length and pointed in the same direction, it's the same vector. It's just a copy. So vectors are place independent. Questions? There is one vector that's the exception to this. The zero vector. A vector whose length is 0 I'm standing here and I'm going 0 feet forward. Is that any different than going 0 feet backwards? 0 feet left or right? It doesn't matter at all. So the vector whose length is 0, the 0 vector, doesn't have a direction. The only exception to a vector having two quantities attached. If vectors are place independent, then putting one with its initial point at the origin, like AB as opposed to CD, might be beneficial to us. And we'll call a vector whose initial point is at the origin in standard position.
What do you call the point at where the vector leaves from?
The initial point. So A is our initial point, C is our initial point, B and D are our terminal points. Some textbooks actually call them start and end, origin and terminus, whatever. But even if they're not on a coordinate plane, I should still be able to deal with vectors as objects. Oh, goody. I get to think back to what I've taught you all discrete, or I taught you all in other classes, and I said, well, we have these things we want to do operations on. I now have a set of vectors. Instead of numbers that I'm doing, adding, subtracting, multiplying, dividing, I want to do those sorts of things to vectors. How does that work? There's a geometric interpretation of vector addition that literally all you have to do is draw. Vector addition means do one after the other. So if I have two vectors, V and U, notice I've deliberately made them different, although we can't add a vector to itself, that's fine. In order to add these two vectors, we're going to move one to the end of the other. So the initial point of one overlaps the terminal point of the other. So which one do you want to move? Okay, if we move V, then I have V here. So the initial point of V is now at the terminal point of U. And then adding them goes from the initial point of U to the terminal point of V. Hello. I'm using these little arrowheads above my vectors, these harpoons, because I don't have boldface chalk. The textbook just uses a boldface letter. You don't have to put the little arrowhead up there, but I find it helps me to know whether I'm talking about a point or a vector. We'll see a reason for that in a minute. Ben, you told me to put V as the one I moved. What if I moved U instead? Wait a second. There's V, right? If I move U up, there's a copy of U. What happens? End up in exactly the same spot. Congratulations, you've just proved a rule without actually doing any freaking algebra at all. You've shown me that U plus V as vectors is the same as V plus U. I hope it is no one's surprise that we call this addition rule a parallelogram rule. The two sides involved here are parallel in each behavior. I have parallel U's and parallel V's because that's what the copying does. It preserves the direction. Big chunks here. All right. In order to adequately define other operations on vectors, my best bet is to define, rather than a subtraction first, a multiplication. My goal was to differentiate a vector from a number. So I'm going to call a number scalar. S-C-A-L-A-R, a scalar field. As far as we are concerned, almost always this is just a real number. Because we are using real numbers in our vectors, we usually refer to these as vectors over the field of the real numbers. So you'll sometimes hear this referred to as a scalar field. Fields have a particular definition in abstract algebra. Don't worry about that. Given a vector v, I'm going to multiply that vector by a number, not by another vector. I'm going to multiply by a number. What's that going to do? I'm multiplying, I'm going to change something. This only changes the length of my vector. It doesn't change the direction. Now I need to be specific here because it could change the direction in one very specific sense, but it ends up pointing in the direction parallel. It depends on what number we use. Well, really, it depends on the sign of the number we use. If C is positive, we make our vector longer or shorter and point in exactly the same direction. But if C is negative, then I point in the opposite direction. While that's parallel to, sometimes people actually call that anti-parallel because it's pointing, quote, the other way. And vectors have an orientation, but it's along the same line. It's just whether we point in the same direction as our starting vector v or in its opposite direction. What's missing?
Is equal to.
And what happens when c equals 0?
It says that.
I get 0, don't I?
Yeah.
What direction does 0 have? It doesn't have a direction. Aha! So that's another result that I can actually say shouldn't even require a proof. If you have 0 times a vector, you get the 0 vector. You've shrunk your direction, your length to nothing. Therefore, you no longer have a direction anymore either. If C in absolute value is larger than 1, our vector gets bigger. If C in absolute value is smaller than 1, our vector gets smaller, regardless which direction we point. That allows me to make linear combinations of vectors. So I take number times vector plus number times other vector, like I did here. I can add, and if I have a negative value of C, that's how I subtract. The opposite of a vector is -1 times that vector. You take the length and keep it the same, you just turn the direction around. Then that would actually be the same as interchanging the initial and terminal points. You'd be basically putting the arrowhead at the other end. And once I have this negative idea, then I can say that u minus v is the same as u plus -v. Which in this picture, I think might be helpful for us to actually do. If that's u and that's v, where's u minus v? I'll do it exactly that way. I'll do u plus -v. So I'll start by reversing v. And then I'll make a copy. U minus v. Interesting note. Remember that vectors are position independent? What do you get when you do v plus u minus v? I get u. But that means if I take this piece, that's u minus v, and I put a copy of it up here at v, it lands right here at u. It's the other diagonal in our parallelogram. So u plus v is one diagonal, and u minus v is the other diagonal. Sneaky mother. Questions? There's no axis over there. There's no numbers. There's no Cartesian anything over there. This is not helpful. In 2 dimensions or 3 dimensions. That funky r is the real numbers. So r squared is the Cartesian plane, 2 directions. R cubed is 3-dimensional space. Then I can put numbers on all of this. And it turns out that if I use my vectors in standard position, then the initial point is always the origin. And I can uniquely define a vector by telling you where it ends. We can describe a vector completely in standard position by its terminal point and its terminal point only. So the vector we had earlier, AB, where did it end? The one that was in standard position. 3, 7. So I would say that if that's my vector AB, I really only need those numbers. But I need somehow to indicate that this is in standard position. Doing so is usually written with angle brackets. And these numbers are now called components of my vector. Well, look at the vector we had that was written CD. CD started at -2, 1, and ended at 1, 8, right? And we said that that was the same as the vector AB. So in components, it should be the same. How do I get that vector from these points?
Taking the difference.
That's all the components are, is they're the difference between the terminal and the initial point. And it's always terminal minus initial. So there's the vector CD. And lo and behold, the components are the same. So I have another way of saying, hey, look, AB and CD are the same vector. This is often referred to, in addition to calling it components, we call it a position vector. Because it's not telling us where we started, where we ended, it's measuring a position in space. By default, putting it at the origin to start is what we tend to do. Questions? Fumble. I'll pick it up after class. It rolled onto the podium. I don't want to dig for it right now. I've done this all in 2 dimensions. You know what changes in 3 dimensions? You get another number. That's it. If A is 2, 3, 4, and B is -2, 1, 1, what's the position vector AB?
-4, -2, -3.
End point minus start point. -2 minus 2, -4, 1 minus 3, 1 minus 4. Where is that vector? Where is it?
8th option?
Say again?
Is it the 8th option?
1, 2, 3, 4, 5, 6, 7, 8. That way. -4 is back. -2, -3. But that's technically the 7th octave, right? 1, 2, 3, 4, 5, 6, 7, 8. Gotta remember which way I'm going around. And it's easier for me to just say behind, right, and down. How long is it? What's the length of that vector? Wait a minute. Distance in 3 dimensions. The length of the vector is the distance from the initial to the terminal point, right? Didn't we talk about distances yesterday? What's the distance in 3D? Say again?
Square each number and square that one.
Aha! Because we're taking that number minus 0, because the initial point is the origin. So, if we have a vector whose components are v1, v2, v3, then its length, we'll use absolute value. Some textbooks will sometimes use a double absolute value bar. You'll see a lot of sources that use that. I will slip up regularly and use a double. Either way, it's the same idea. This is the length. Some square and some square root. Pythagoras. More. You'll often hear this not just called length, but norm or modulus. Yes, I know we use that for modular arithmetic. We use a lot of the same words in a lot of different places in math. The other good part about this is my operations of adding and scalar multiplication when dealing with components literally become component operations. So I'll go with -4, -2, -3 because we already had that vector. We'll call that u. And then I'll come up with a vector v. How about -2, 6, 7? If you add these vectors, then all you have to do is add the corresponding numbers. You subtract these vectors, all you have to do is subtract the corresponding numbers. You multiply by a scalar, all you have to do is multiply each number by the scalar. So, 2u minus 3v. Wait, reverse the signs. Let's make it -2u plus 3v. All right. -2u, multiply each of these numbers by -2, I get 8, 4, 6. Add 3 times each of these, -6, 18, 21. When I add, I get 2, 22, 27. I like working in components. It's much easier. Questions?
Still the same when you go with high dimensions as well.
Yeah, as long as we're using what we refer to as standard Euclidean operations. But that was what we did in linear algebra, right? We took all of this and put in as many dimensions as we want. But there are some things that we might have to tweak. This actually gives me a more general definition. With these two operations, adding and scalar multiplication, a collection of vectors obeys a bunch of rules we really like, the same rules that we use for numbers. That makes it what is called a vector space. That's why I was talking about abstract algebra, where we talk about all of these closures and fields and things like that. When you add two vectors, you get another vector. When you take the scalar multiple of the vector, you get another vector. So we have that, and then we have a list of properties. We've already seen two of them. If you add, it doesn't matter what order you add it. If you add 0, what happens? Nothing, right? You don't change your length, you don't change your vector direction. What should the component version of the 0 vector look like? I promise it's not a trick question. But that's a number. What should it look like in components?
Would it like just not exist?
No, we have to have components for every vector. But if I have a 0 vector, unless I can write a 0, then it should have no length and no direction, right? Well, then it's got to be 0, 0, 0. So if you add it to anything, it doesn't change, right? If you add v and minus v, you should get 0 back. On page 802 in our textbook, there's a list of properties of vectors. And it's things like commutative rule, associative rule. If I do the vector A plus the vector B plus the vector C, and I put parentheses around the B and the C, that's the same as if I do A plus B first and then do C. And we could go through and write out proofs for all of this, if we really wanted to, in components and show you why these rules have to be true. But there's a list of 8 rules on page 802, and they all work this way. Every vector we want works this way. Questions? I keep doing this with my hand. But it's more than just remembering what the axes are. It's also a way of thinking about my vectors. In components, we can think of a vector as we go forward or backwards according to the x direction. We go left or right according to the y direction. We go up or down according to the z direction. So I could consider this vector, or any vector we've been using, be broken down into 3 pieces. The x motion, the y motion, and the z motion. So in one sense, these 3 vectors form a fundamental set of vectors for us to build other things out of. We're going to call this the standard basis for 3-dimensional space. By the way, if you have 2-dimensional space, then you just have the first 2 and they're only 2 units long, right? So I have an x direction and a y direction, I wouldn't have to worry about a z. These get names. This first one is called I. The second one is called J. The third one is called K. And sometimes instead of little vector arrows on top, some textbooks use a hat. You'll see that more in physics papers and in science papers. Chemistry does that a lot. But they're still the same thing. And when you get more of them, like if you said we could use as many dimensions as we wanted, then they stop trying to use letters and they start using numbers. So you'll see this one, E1, E2, and E3 for elementary. But that means I can take a vector and turn its component form into a combination of these. So the vector up there that's V, -2, 6, 7, can also be written as -2i plus 6j plus 7k. And we'll actually come up with places where ijk form is preferable and places where component form is preferable. It depends on which you like better, but since we'll see both and we'll use both in different places, I wanted to introduce them now. This is often just called an ijk decomposition, but I tend to think of it as a basis decomposition. That's why I wanted to use that word over there. Questions? Talk to me. There's something else nice about these vectors. How long are they? I, J, and K. They're all 1 unit long. As a matter of fact, any vector whose length is 1 is called a unit vector. And unit vectors are used to indicate direction without indicating a length. Remember, we said we had length and direction, so I can go this way, and then we could tell you separately how far to go. So I could take any vector and turn it into a unit vector. That vector is not a unit vector. What is the length of this vector v? Square root of 3. Okay. I would like a unit vector whose direction is the same as v. Or no, it's got to point into the first octant, 1 unit forward, 1 unit left, 1 unit up. There it is right in front of me. My elbow's the origin. How do I make a unit vector? That's bigger than 1, right, in length? So I need to shrink it. How do you make a vector smaller? I need a scalar. I need to multiply by something that will shrink it down the right amount. Or if I needed to make it bigger, I'd multiply with something to make it bigger, right? What's the right number to make this shrink down properly? 1 over root 3. That's a unit vector. Because if you square these lengths, you get 1/3, 1/3, 1/3. Add them up, you get 1. Take the square root, you get 1. That's true for every vector. As long as the vector is not 0, 1 over the length as a scalar times the vector will give you a unit vector. Clearly, that's not going to work when v is 0, because you get a length of 0, and then if you divide by 0, your calculator goes. By the way, what if I wanted it to go in the opposite direction? Negatives make me go in the opposite direction. So if 1, 1, 1 goes this way, negative 1, negative 1, negative 1 goes the other way. Put a negative in front of that, and it goes the opposite direction. Talk to me. I was a physics student before I was a math student. My favorite applications for vectors are all physics-based. Page 804, example 7, shows a weight hung from 2 wires. So I have a roof. And I have a mass. And what they tell me is that this is 100, I don't remember what the units are, pounds, sorry. This angle is 50 degrees, and this angle is 32 degrees. If I tell you that the breaking strength on each wire is 70 pounds, can they hold that weight? What if the breaking strength on those wires is 80 pounds or 90 pounds? How much force is being pushed into each wire? Oh, shit. How am I going to figure that out? I'm going to cheat and turn everything you see here into vectors. What I'm going to do is I'm going to put the origin at the spot where the weight meets the ropes. It's two-dimensional, but I could do it with 3. Z is not going to help me at all because this is static in the plane. This is referred to as static equilibrium. Nothing is moving, nothing is changing, it's all perfectly held still. But now I say, oh, there's a tension in this rope. There's a tension in this rope, and there's gravity pulling down. So I have 3 different forces. The force due to gravity, which one did they call tension 1? They call tension 1 the one on the left, and tension 2 the one on the right. But now I can say, oh, if this is 50 degrees up here, then that's 50 degrees also. And this is 32 degrees. And you can now write in I and J vectors for all 3 of those things. Let me start with the easy one. The force of gravity. The force of gravity points down. With 100 pounds, pounds already take gravity into account. I don't have to worry about multiplying by G. We're not in the metric system. I apologize. So I can say that the vector for the force of gravity is 100 J. Wait a minute. Which direction does J point? J points along the Y direction, right? So J should point up. My force is pointing down. This should be negative. Let's look at tension 2. Why did I pick tension 2 to start with? Because according to the way I laid out the x and the y-axis, it's in the first quadrant. So tension 2 would have an I and a J. There's the I part. There's the J part. going in each direction, right? How do I get the length of this part? Ooh, I got to go all the way back to trig. It's a little right triangle, isn't it? So I have T2 there. I've got 32 degrees here. If I want the horizontal piece of this, I use the cosine. It's number T2, the length of the vector, times the cosine of 32 degrees I. And then the vertical side will be J. Length of T2 times sine 32 degrees J. And that's going up, that's positive. I can do the same thing for T1, right? T1 is length of T1 cosine of I plus length of T1 sine something J. What angle do I use for T1? If I use 50, I need to be careful. Cosine of 50 will be positive. This angle points in the negative x direction. So the way to get around that is to measure the angle from here, which would be 130 degrees. Now, I said we were in equilibrium, nothing was moving, right? That means that the I parts have to balance each other out. If I add them together, I should get 0. And the J parts have to balance each other out. If I add them together, I should get 0, which gives me 2 equations in 2 unknowns. The 2 unknowns are the length of T2 and the length of T1. And that's the amount of force on each rope, which means I can tell you whether or not it's going to hold. That algebra is on page 804, and it turns out that the rope on the right, tension 2, is 65 pounds. The rope on the left, it's almost 86 pounds. So much more tension is on that left rope than on the right rope. And that means I have to be careful. Find the breaking strength of my rope. Tensile strength, because I'm pulling. Take this entire process. Instead of ropes, let's use chemical bonds. You've got activation energy. How much energy does it take to break that bond? How much energy is stored in it is literally the chemical equivalent of tension. I can tell you how much it takes to pull a hydrogen atom off of methane by looking at this. Only those bonds are in 3D, not 2D, but the process is exactly the same. And I've run right up against the clock. So I will see you all tomorrow. And I'm going to figure out what is going on with my camera, and then I will let you know. I'll post these for you all, my short notes. Mistake because I didn't write anything, but I basically wrote it all here.